forgot to turn on the microphone last time, but yeah. Shall we continue? Okay. So I hope everyone can hear me on Zoom. Before we go into the next topic, which is reinforcement learning, I wanted to actually show you something like another study we did, which had some really crazy results on ensemble methods, which I thought you might be very interested to show in the class briefly. This was a competition we ran 5 years ago on machine learning models that had to predict Alzheimer's disease. So here we had. This was a study, so you can find the paper on my website. This is called Tadpole Challenge. And we ran this 5 years ago in 2017. Back when I was in London, let me show you something really interesting. So the key task here was so you had a set of 1,600 subjects that had Alzheimer's disease. And you had to predict, this was a training set. And they had this was a number of, overall number in 3 different categories. These are healthy people, healthy subjects. These are in between. It's called mild cognitive impairment, and these are Alzheimer's disease, so AD. So it was a classification problem, for example, to classify which one had Alzheimer's, which one was healthy, and which one was in between. And we had quite a lot of data on it, so MRI scans, some other types of scans called PET scans, and several types of PET scans with different tracers here, diffusion tensor imaging, and so on. So look here. Look. These are all the participants in our study. So we had a total of 63 methods that were submitted by international teams. So look at all them. And So some of them were support vector machines, some of them were random forests. We had linear regression, we had linear mixed effects models, feed-forward neural networks, semi-temporal random forests, which are some kind of random forests that have the time into account. We had a regression ensemble, an ensemble of regression models, ensemble of regression plus hazard models, LSTMs, long short-term memory network models, all kinds of models. Bayesian classifiers, disease progression models, gradient boosting methods, which are also a type of ensemble methods. So quite a variety of different models. So not just this is not even about different data sets that they were trained on. This is like actually using completely different frameworks of thought. And what I wanted to show you is these are the results that we obtained, that the participants obtained. So it's a whole table of results. And what we did, one of the things we did when these results came out is that, so you see on the left-hand side, you see all the teams with all the methods, all the algorithms that they submitted, their performance, their ranking, their diagnostic performance. This is a performance metric, and same for the other 2 problems. These gray methods I wanted to highlight. These are consensus methods. These are ensemble methods. We literally average. So the mean here, this particular mean is basically we took all these submissions and we averaged the predictions. And look, it got almost top performance. And we took the median, it got top performance out of all of them. So even though each individual submission had much lower performance, and it goes all the way to here, taking the median or the mean, averaging all the submissions, give us top-notch performance. Isn't it crazy? It's averaging over the predictions of these models. So each of these models were making predictions for each patient. So we had to make predictions for 800 people, 800 patients. And we average like...
How much in the data set? The data set did they use?
What's the data set?
Mm-hmm.
The data set, it's a data set called ADNI, the Alzheimer's Disease Neuroimaging Initiative. It had a lot of data for multiple modalities from these patients. Um,
You guys tried different models for each specific one of those, or like did you just?
did we try different models for each specific one of those? What do you mean by that?
I guess data sets. I might be a little confused, but like
Yeah.
on the above one, right? You had like a specific one for each like row, right? On the,
So each row has a model, has a particular submission from a team that made it build a particular ML model.
okay.
But what are you trying to? No?
I got it. So like yeah. So you guys just averaged.
We average all the predictions. So now each model had then to make predictions for 800 for the test set. We had a test set that we tested on. So they had to make predictions for those 800 subjects in the test set. And then we average all those predictions across all these models. The significance of the colors. So the colors, what they mean is the type of method they ran. So green meant that they ran generally a disease progression model, which is a type of kind of like a Bayesian model with latent variables. So that's green. Blue means general machine learning model. Pink means random forest. And blue. Let me show you. I have the legend here. Sorry.
Which one's your team?
I was organizing. Yeah. So look, blue regression models, proportional hazards, pink random forest, blue neural networks, green disease progression models. These are basically again Bayesian models with latent variables. That's what this means. Machine learning other. These are benchmarks. So that's what the colors mean. The class of models. So you see, generally, like we didn't see any particular trend in the types of models that we ran. But the key thing is that when you average all of them together, you get top-notch performance. Yes, we have a question, yeah.
What you mean to say is if we have like unlimited resources, we can run a bunch of different ML models on the same data set and then
Yes,
do a meeting
yes,
over them.
yes. Because each individual model has their own biases, but when you average them out, they often cancel out, especially if they complete different classes of models that have completely different inductive biases.
But this
Yes.
isn't like really practical, right? Like
No, it's not.
running
It's
all
not.
these,
It's not.
like,
Yeah.
This is like like hey, it's cool, but like we're not.
I mean, it's an ideal scenario if you have unlimited resources.
Yeah.
But I wanted to show you because I think sometimes people don't people underestimate the power of these ensemble methods. Again, like you, and let me tell you a few more surprising things. Like for example, I tried because I did all of these, and I remember I tried just averaging the top 10, let's say, because those were, let's say, the better ones, and it didn't give these ensemble methods didn't give as good results. So you had to average. It was much better to average all of them, even the weaker ones that didn't perform as well.
Which means if you had more participants, it would be much better as well.
Yes,
I mean, it's kind of
yes. Yes, so it's very surprising, yes. But this is, yeah. Let me show you something else, another really surprising issue. Look at this row here, this randomized best. Can someone guess what that might mean? What that randomized best? What a randomized model might mean here? Yeah, but how exactly? Just give a wild guess. Randomly choosing a prediction. So this was what this meant. What this meant is that what if you do random guesses, completely random predictions? You choose a random diagnosis, and we build like 100 such random models with random guesses, 100, and we chose the best one. So the idea is you build what is called a null hypothesis, a null model. Have any of you heard of this concept of a null hypothesis in statistics? You're often trying to find if these results are actually like meaningful. Like for example, how do these models, for example, down here compare to like a random prediction? What if you randomly guessed the diagnoses? This is what we did with that, and what we found was that you see how a lot of these models, even further down, did not make predictions significantly better than random guesses. So actually, a lot of them were also even completely random, almost didn't give too much meaningful. It wasn't significantly better than random. Isn't it crazy? Let me show you. You go ahead. Another question. Yeah.
I'm trying to understand a bit the randomized testing.
Yeah.
The idea is that we make random guesses and we get score to prove that none of the modeling has any benefit really?
Kind of, yes. Kind of. Like you're trying to compare with how a random. Let me show you an example. I think it'd be best. Let me do an example here on the board. So. Imagine if you just have an axis like this, or a one-dimensional axis, and I'm doing this on top of my head, so this is quite like I haven't prepared this, but imagine you have a model here, like this is your model 1 performance, for example, which is here. So this is 1, this is 0, so this will be like 100% accuracy, let's say, and this is 0% accuracy, for example. So you're here. Now, for example, if this is a binary problem, now like on average you would get 0.5 prediction, right? If it's with a random guess, we get a 0.5. So what if you take, this is on average, right? But what if you take multiple random guesses? If you take multiple, you see that some of them will land here, some here, some here, some here, and so on, like this, right? Like if you take multiple, like if you take 100 different random guesses, they won't all, because you have to predict 800 people. So you won't guess like, exactly like 400 correct, 400 wrong. Some of them will have 380 correct, and then the rest wrong, and so on. So then what you do, you build take these random guesses, and then you fit a distribution onto these random guesses, and this is called the null model. Null model or null hypothesis. So it's the same, null hypothesis. Yeah. So now the question becomes, under this null distribution, what's your model here is at a particular threshold, and what's the probability that this null model was significantly better than these random models? Does that make sense? So sometimes, for example, and people do these null tests, for example, and they say, oh, if this area here is smaller than 5% under a p-value of 0.5, then you say that it's significantly different. So whatever it is. So we took a significance of 1%, not 5% there. So we took and that's the threshold. So for this, what this shows, this randomized best shows, is that all those models below that randomized prediction was basically this threshold. For example, this randomized best was this particular threshold. So everything below here was not significantly different from the null distribution. It's a test, yes. But that's sort of the threshold. So everything below here is not See, it's below the threshold, so it's sort of like, it's not significantly different from this distribution. So basically what it means is that they could have achieved those results also by guessing.
Even the family that those models use so much complexity.
Yeah, exactly. And they use so much complexity and so much effort, and yet, like, for example, some of them are not significantly better than random guesses. So you would have been probably equally well doing just random guesses on some of the tasks. That's what it means. Yes?
I have a quick question. So if you split up the two diagnosis matrix, what's the relationship between the MAUC and BCA?
They are two different performance measures to measure it. So MAUC means multi-class area under the curve. So if you might have seen have heard of area under the curve. Which of you have heard of AUC measures? Under the curve? I see a yes here. Okay, but not too many. It's basically it's a measure in machine learning of modeling performance with also when you have uncertainties in the predictions. And multi-class simply means you do that in multiple classes, sort of thing. And BCA is balanced accuracy, balanced classification accuracy. So it's like the accuracy measure you calculate just balanced for the data set, especially when you have a highly imbalanced data. Like if you have too many of one class and low on another, that's what. So they're kind of similar, but they're not exactly. Yeah, you see sometimes there's some differences. So this model has the top score in BCA, but not the second highest in MAC, for example.
How so they're similar?
How so they're similar?
Yeah. No, the MAUC and BCA. How are they similar?
Oh, they both measured the diagnosis, the accuracy of the diagnosis predictions. So theoretically, they're not similar. One of them is an accuracy, one of them is an AUC measure. But because we ran them on this variable, on the diagnosis, that's why we put them in the same column, because they both these are other. This is a cognitive test, so it's completely different from a diagnosis. It's like when, and this is a ventricle measure. This is a brain measure. It's a structure in the brain that is highly sensitive to the Alzheimer's disease. But anyway, let me share something really briefly before we, because this had some very interesting results. So another thing is, now look how the results changed slightly when we ran on a slightly different data set, when we ran on just a single time point for each subject. Now you see how the consensus mean are is also on the very top, and we have different kind of teams and slightly different models that actually performed better. So it's not it's not exactly the same ranking anymore when we run on a slightly different data set. The same models, exact same models, exact same predictions. Just the data set changed now. So you see how the ranking changed when we did that. A final thing I want to show you also about ensemble methods is this. Look at this plot. So this plot shows the bias in each model across all the patients. So these are all the ML methods. These are the subjects in the D4 test set. So we had around 100 subjects here.
So yeah, it's not 10 subjects, it's subject 10 kind of thing, right?
Yes. So these are different. It's like 100 different people with some with MCI. These were only the ones which had this particular class. These were the ones in between, which were not entirely healthy, but also not fully Alzheimer's. And look how, what I want to show you, look how some methods consistently underestimate the bias. So they have a bias towards, so if the subject had an MCI was in between, they were consistently biased towards healthy. They were consistently saying, oh, these are healthy people all the time, kind of, across all these subjects. Whereas some other models, like these ones in blue, look here, these are overestimating the bias. So they're saying these have Alzheimer's. All of these have Alzheimer's, most of them. So there was a clear bias across all the people here. The models were biased towards one way or another, for example. Does that make sense? But the idea is, again, when you do an ensemble, we average together all these biases. So these underestimates or these overestimates, underestimates in red, over in blue, they would cancel each other out. So then you get a much more unbiased estimate. Yeah. Same here for a different, for ADAS again. This is the error. So white is when you have almost zero error, but red means severely biased towards underestimating it, underestimating the severity, and this is overestimating it. So look how some models again consistently overestimate across all the subjects, and others consistently underestimate. Okay. Any questions on this? Yeah. All right, let's continue. So we have 10 minutes left, but let's start briefly introducing the idea of reinforcement learning, which is a very fun topic in ML, and we'll continue next time. So reinforcement learning is reinforcement learning is a very key and cornerstone topic in machine learning, and essentially here what we've been doing so far is that we've been fitting models on static data sets. They are static data sets. They don't change the data set, and however, in reinforcement learning we have a much more sophisticated paradigm where we also have an environment, and now this environment is allowing us to collect new data points and take actions. How many of you have heard of RL, reinforcement learning? Roughly, okay, a bit more than half. Okay, great. So you're so familiar. So the agent receives some feedback in the form of rewards. So the key idea is that the agent, of course, you have a robot that runs in an environment. It takes some actions and then also receives rewards for those actions. And we will define shortly that also these rewards by a utility function. And the key idea is that they keep doing this in a loop. They take an action, and then they take another decision and an action and decision and so on, and the environment around them keeps changing as the agent takes actions, moves to different states, and so on. And the key idea, what we want to do is to maximize the expected reward of this. So here's an example. So an example in RL is to play a game, for example, to play chess, for example, or to play Go, or some of these games. So again, you have two players, which are two agents, and they all take actions, and at the end the reward is whether they win or lose the chess game, for example. Also a scavenger hunt. So for example, you get different multiple rewards and along the way, and you have and that's your objective is to maximize those rewards and to and of course, before we actually, can someone give me other ideas? What are other ideas of reinforcement learning? Like what could be an agent? What could be an environment? What could be the reward? How can we model real life phenomena with RL?
Can you repeat the question again?
What are other examples of agents and environments in the real world where which we can model with reinforcement learning?
If we want to solve any problem we don't have a data set for, we know that it can probably learn from some good or bad behaviors. And then it can automatically,
so solving a problem we don't have a data set for, and the model and the agent can learn from good or bad behavior. Yes. But like what exactly? Like what? Give me a scenario. In the real life. Yeah. Teaching a dog new tricks. Very nice. Yes.
Teaching people new tricks.
Teaching. Yeah.
There's these models that make a point,
Uh-huh.
but then you
Uh-huh.
take more time to get to the end. So there's a lot of like in side scroller games, a lot of rewards and costs there. But then they repeat the model again and again and again.
Yeah.
And
Yeah. Yeah. Yeah.
maximize this.
Yeah.
Yeah, I guess because you don't have the data set, you need multiple iterations to figure out what's right and what's wrong.
Yes. 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 What about robotics?
Yeah, I was thinking of autonomous vehicles as well.
Yep.
Autonomous vehicles.
That's the same
Yes,
applications, yeah.
autonomous vehicles. Yeah, robotics. Yes. What about again? What if we go to a healthcare domain? What could be something in the healthcare domain?
Well, with these more and more, I guess, advanced prosthesis
Uh huh.
and things that try and read signals from whatever's left of that limb.
Advanced prosthesis. Yes. 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 Exactly. Exactly. We have so also surgical robots again, like robots that perform surgeries. Again, the same thing. They're trying to maximize the reward, which would be to do this the operation they're trying to do. Or another example would be, for example, what about scanners? Can medical scanners be sort of like an environment? Yes. For example, you can model like they have to make decisions on what to scan. For example, do you scan the top slice of the brain or the bottom slice or the middle and so on? And those are decisions, for example, and the environment is that. So they can decide what to scan and so on. So you can model all these kinds of things with reinforcement learning, with this kind of paradigm. And before we will go into too much detail, we will of course we'll understand, go through markup decision processes in order to get this. But before that, let me show you some examples to motivate. And I think I need to be on a laptop for this. So this is a robot that was run at the ICRA conference. So this is a famous robotics conference, and it was in 2004. And this is initially the robot was not able to walk too properly because it wasn't trained. But after training and learning, it was able to learn to walk much more efficiently. So let's see how it looks. And let me put on the sound. So can you all hear? So you see how initially it's walking quite. It's not working well. It's not working well. Like it's struggling and it takes a long time. You see, it kind of wobbles, like it slips a lot. Sorry?
It's not using its feet. It's like on its forearms.
Yeah. So, and this is during training, for example, and it's loading. One sec. These are videos. Where did the sound drop? So you see, during training, this got a bit better, but it's still it still slips a bit. And at the end, again, it freezes for a few seconds until it loads it. Okay. So now at the end, it. See, now it learns much better to walk much faster. It doesn't slip anymore. And
was there
after training,
it never kind of went up onto like its feet with the front legs? It seems like you could stand up more on the front.
Yes. I don't know. Maybe it was designed to work like this on these, and not on that.
Maybe it's harder to balance.
Probably, yeah.
I thought maybe from the very beginning it could balance like this and at least move a
Yeah.
little, so
Yeah.
just walk based using
Yes.
kind of form rather than standing up there.
Yeah, okay, so I think I also had a quiz for today, but we won't have time to go through it, so we'll do it next time. But we have a question?
Yeah. So like I'm a little confused. Like how are they like tweaking its changes, right? Isn't it like a program running on the like dog to like make it go?
Yeah, there's a program running on the robot, and the program is assessing its progress towards the objective. So in that case, is how much it moved forward, like, and how fast.
How many
So,
steps it took.
and how many steps it took, these kinds of things.
Adjusting within.
And it's adjusting within while it does it. Yes, yes.
So they're just kind of having one. They're kind of running the program a bit and then stop and have it walk.
Yeah, 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 yeah. Yeah, well, we'll continue next time. It's a really interesting topic. Yeah.
At a conference where they were showing reinforcement learning for video games.
Sorry, say again.
I was once at a conference where they were showing reinforcement learning for video games.
Uh-huh.
And, they were making models that could do like League of Legends, Super Mario.
Right.
And you know, like okay, Super Mario is like a side-scrolling. But you know, League of Legends is like almost 3D. There's so many different actions, and there were like players who could, like AIs who could beat other players. I don't know whether you've looked into that.
Well, what conference was it?
It was when I was in when I was in another company. It was like an online thing that they signed us up to. I don't remember the name of the conference.
Uh-huh.
Let me show you some videos. It's really, like,
Yeah.
it's more fun.